Urban infrastructure like potholes are often underreported, delayed in response, and poorly tracked across systems. We start with the Geo Explorer dashboard. This is a live interactive map. Here, currently we are viewing Boston, where previously reported hazards are already visualized. Now, I can report a new pothole directly from the interface, and with a single action, this gets pushed into our backend pipeline and queued for processing. Here, we can see that we have switched to our maintenance dashboard. We can see all the incoming hazards in a structured queue. This interface is designed for authorities, allowing prioritization, tracking, and efficient dispatch. Instead of scattered reports, everything is unified into a single actionable system. Now, we activate our AI Copilot. You can see here that I have asked which hazards need urgent attention, and the system analyzes clustering, frequency, and severity, and highlights priority zones. This removes manual filtering and helps decision makers focus instantly on critical areas. Next is our detection pipeline. Here you can see that I have uploaded a video, and our model pre-processes the frames and automatically detects potholes in the scene. This is not just detection. Each identified region becomes an actionable entity. Clicking on any detection allows immediate reporting, bridging raw data to real-world action. Coming to our hardware implementation, this is our Raspberry Pi 4 based edge node. Our goal here was simple. Can this entire pipeline move beyond cloud and run closer to where data is generated? We tested and deployed a detection workflow directly on Raspberry Pi. This includes video ingestion, pre-processing, and running inference on device. Why this matters is latency and scalability. Instead of sending all data to centralized servers, edge nodes can process locally and only transmit meaningful results. This reduces bandwidth usage, improves response time, and makes the system deployable in real-world environments like smart city grids or vehicle-mounted units. We have demonstrated the full pipeline running both on a development machine and also on an edge device.
This is the network surveillance view, where we can analyze sensing coverage across different regions. The map is divided into geospatial grid cells that represent sensing coverage of distributed nodes. Using the network intelligence agent, we can analyze a node to evaluate network activity, geographic spread, and sensing performance. In this example, the analysis shows that the selected region currently has no active sensing nodes, indicating a coverage gap where the additional sensing nodes may need to be deployed. So, how do we actually scale this? Let's tie the edge hardware to the blockchain. First, the driver connects their wallet. We designed this to be completely zero touch for the user once it's set up. Here's a live feed running through our pipeline. Watch what happens when the AI spots a pothole. It detects it, grabs a spatial hash directly on the device, and fires the payload to our cloud. It clears the deduplication check and switches to verified. This is the trigger for our Solana smart contract. I'll click into the reward here. It drops us straight into the Solana DevNet. This is the DePIN scaling engine in action. You can see the exact transaction signature right here. The contract just autonomously fired a micropayment to the driver's account for validating the hazard. You can see the balance update in real time. We are processing these validations for fractions of a cent. You can't do this through a traditional bank, and you can't do it on a slow blockchain. This is the real-time infrastructure maintenance verified by the cloud and paid out instantly on Solana. We are VIGIA. Thank you.